So today I will start the lesson on bias and variance and how to address it using regularization. Right. So let me share my screen first. Okay. Uh, so can you see the full screen? Can someone talk because I can't
Yes.
see you?
Yes.
You can. Right?
Yes,
Thank
sure.
you. Thank you. Thank you. Okay. So today's lesson is lecture 7, bias, variance, and regularization. Actually, when it comes to the theory of machine learning, I can say this is the most important theory in whole machine learning, right? Uh, because this is what really differentiates from a kid in machine learning who knows how to type machine learning code to a real data scientist who can actually do something with data, right? So that means uh, what you know, right? So when you have learned some machine learning algorithms, and when the code is there, you can simply apply this code. You can generate some code with some generative AI, and you can apply the data, and you can generate some results, and you can get actually, if you are fortunate, you can get some result, some higher accuracy. But uh, when you have some issues, right? That means you are not getting the expected level of accuracy, and you see there is some problem. How should I address this? What should I do to increase my accuracy? Uh, I have this data. I am using this particular machine learning algorithm. What should I do? Should I use another algorithm? Should I change the parameters? Should I increase the data? Or are my data not that accurate, or is it noisy? What is the reason behind the problems that I face? Uh, or an ordinary machine learning user may not know how to handle these problems, right? But if you become an expert in machine learning, you should be able to identify uh, the problems that you are facing and why it is causing these problems. And you should know what are the things that you have to do to get rid of these problems, or the minimize the effect and improve further from the current status of your machine learning project, right? So these are the concepts that are used to get that knowledge. Unless you understand these concepts well, you won't be able to uh, do what a professional data scientist or a data analyst or whoever a professional can should do with data, right? Uh, when you want to get some result, you have a bunch of machine learning algorithms in your toolkit, and you have got some data. You should know once you have tried a certain machine learning algorithm with your data set, once you have applied a certain machine learning algorithm and you get some result, and you should know where should I move. That is what you should learn with this lesson, right? So bias and variance are very not that difficult in conceptual level, right? But that is kind of a, that is like the sea, right? So like the ocean, you it's shallow in the beach, but when you move into the ocean, it goes deeper, deeper, and deeper, and you will find that the average depth of the ocean is around 5 kilometers, right? So but yeah, don't get afraid, but once you understand the concept well, you can do it, right? So that is why I have dedicated this whole lesson for these two concepts and the regularization, which is uh, how it is handled. So that is a technical way, right? The bias and variance are concepts, right? So these are very small concepts, but you have to, I mean, you have to conceptually understand what the bias and what is the variance and how it happens. Uh, in my problem, in my machine learning project, which of them are making problems and what are the steps that I have to do as the next step. So when you move into the next step of your machine learning project, you have to look again and you change your path accordingly, right? So that is the importance of this lesson, right? So if you ask in this lesson, if you have any questions, you can ask and you can clarify it, right? So in most of the machine learning lessons that you find in internet, so they are these things are explained in mathematical sense, but uh, this that will not really help you to get to what I have get to the point that I have explained, right? So I am trying to give you the intuition what is bias and variance mainly in this lesson, and you should be able to get that uh, intuition, and then only you will be able to use these concepts for your machine learning projects, right? Okay, too much introduction, but that is required to start the lesson, right? Okay, so let's remind what we have done, right? About machine learning. In the machine learning process, what we do is, right? You get a data set and then you partition your data set into two pieces. One is a large partition and another one is a smaller partition. The larger partition is used for training the machine learning model with the machine learning algorithm, right? And once you have trained this with the algorithm, the data partition, which is known as the training data set, right? Training set, and then you get the machine learning model, right? So once you have got the machine learning model, you have to make sure that your data is that your machine learning model is working well for unseen data uh, from the training time, right? That means when you have trained the machine learning model with the training data set, you have to use some other data which is not inside the training data set and test with the machine learning model, and then only you will understand how accurately the machine learning model is working, right? That is clear, right? That is why we are using the remaining data partition, which is known as the test data set, right? We'll use the large partition of data known as the training data set for training the machine learning model. And once we have trained, we use the smaller partition known as the test data set for testing, right? And that is known as the machine learning process in general, right? Generally, how we evaluate the machine learning model during the testing, which is known as getting the performance numbers. So there are different ways of getting performance numbers. So mostly used machine learning performance number is known as accuracy, right? Okay, so later we will discuss the performance numbers, what are the parameters, what are the matrices that you should be using when evaluating the performance. But for the now, just think it is as simply as accuracy, right? How accuracy means how accurate the machine learning model, and that means how accurately it can predict the correct uh, outcomes, right? So when we do the machine learning process, this is not a straightforward process, right? That means once you learn the machine learning and when you get the machine learning model, when you select a machine learning algorithm and you get the data set, when you apply it, you train the model, test it, and if you have, then you get a with fair accuracy, and then you stop it. This is not how real world machine learning development process works, right? So in real world, you apply it, that means you apply the data set to the machine learning algorithm, and you get the machine learning model, and you train it with training data, and then you test the model with test data, and you get some number, and then you have to improve the machine learning model so that the performance numbers are increasing, right? So you have to repeat it. You will have to repeat it many times, right? So in each time that you would have to think whether you have to think about data collection again. I mean, if you don't have enough data, or your data is not in the required quality, or whatever the things, right? And then you have to reprocess the data, and you have to view the data once you have collected the data with exploratory data analytics, right? So what we have explained earlier, right, is known as the EDA in short term, right? And then you have to select a suitable machine learning algorithm depending on your knowledge, and then you train it and test it and get the performance numbers and iterate, right? That is the general machine learning process. So when you train the machine learning model, training a machine learning model with data, the same data set, right? When you apply the same data set that you have received with different machine learning algorithms, say that now you are using, for this example, I say that there's a classification algorithms, right? There can be several, right? So one you have learned, right, which is known as logistic regression, right? For example, say you want to do a binary classification. You have to do a binary classification. So the one option is that you can use logistic regression. Another option is there's another machine learning algorithm, right, known as support vector machines. So you can select either one of them, right? So when you test with when you train your data with two different machine learning algorithms, the data that is fitting into your model, actually the fitting into your data can be varied, right? So what does it mean, right? So fitting means your model is, or suppose that you want to do a classification, you are trying to define a decision boundary, right? Or the hyperplane, right? I think you remember what we have done in logistic regression. There we have to define. So what, by training a machine learning model, what we are doing is we are trying to define, we are trying to find the coefficients of a hyperplane, which is also known as the decision boundary for different classes. So how this decision boundary is fitting into your data, right? So suppose, so in the earlier case, what we have learned with the ordinary logistic regression, right? So we are using a flat hyperplane, right? So that means a linear hyperplane. So there you will not see that fitting effect well, right? But suppose that you are using not the linear hyperplane, but you can have a polynomial of so not polynomial that is greater than 1, right? So in the logistic regression, there you are using all the coefficients, or all the x values that are linear, right? So the power of x is 1, right? x1 to the power 1, x2 to the power 2, sorry, x2 to the power 1, and so on. But you can use some, as we have explained, how to use a circular classification problem right? So if you can remember, right? So you have a data set and you have some data like this, and you have some other data like this. We said that we can use a circular decision boundary to, this is not circular, right? So I think this is circular, right? This is circular. So you can use a circular decision boundary to classify these two classes. This is first one class and this is two class, right? So you can use this circular decision boundary to classify. Suppose you are selecting a different machine learning algorithm. Instead of logistic regression, you use a support vector machine. This curve will fit in a different way if we are using a different machine learning algorithm, right? So we will discuss later what we really mean by model fit, right? So that means, for example, say that you have a data set like this. Now, if you build a model like this, this is not that this is a very simple model, right? So this is a model that was fit into your data, right? These are the data points, and this is the model that you have generated with a certain algorithm. And another certain algorithm, right? Say that now, there's suppose you are using another classification algorithm. It is not one that has a linear classification boundary, and it has highly non-linear decision boundary, so it can fit well to classify. So this is a regression problem, right? So don't get mixed up, right? So what we are going to do is we are trying to do a regression here, right? So in this case, we have used the linear regression. So then you can use some polynomial regression with multiple degrees of more than 1 degree of x variables, right? So there you will find a polynomial regression line like this, right? This is the second regression line. So the first one is not that much fitting into your data. Fit means there's a gap between all the data points, but the second regression line, which is not a linear regression, right? It should be maybe a polynomial regression. So this is fitting exactly exactly correctly to all the data points. So now you may think that this one is better, right, than the earlier linear regression. So that is what we are going to discuss in today's lesson. You may not be actually correct. The earlier model has some error, and it is very simple, and the new model, the blue line, has almost zero errors when it comes to the data points that we have learned, but there's a problem with this new model as well. So with the bias and variance, we are going to discuss about these concepts, right? So instead of using these two models, that means without using, so this one is using a certain algorithm, right? And this one is using another algorithm. Instead of using different algorithms, how much the uh, the regression line or the classification hyperplane fits to your data can be dependent on several other factors as well, right? Say now you have a higher number of model parameters, right? Think that you have only two data points. Now your linear regression line can simply fit these two data points 100% accurately, right? The accuracy would be 100% if you have only two data points. But when you have three data points, you can draw another regression line which should not be 100% accurate, right? So that means so actually this is about using the different number of data, right? So in this linear regression line, how many parameters are there? There are two parameters, right? So this line would be a line which has something like y equals mx plus c, right? Or y equals beta 0 plus beta 1 x, right? So there are two parameters, right? Beta 0 and beta 1. When you have increased the number of parameters, say from 2 to 3, right? You may be able to like say that now you can add another parameter like beta 2 x square, right? So using the polynomial regression. So there you can fit your data accurately, right? So suppose this is the new line which has three parameters. Now this new model, this new learning algorithm with three beta parameters can learn it much accurately. But when the model has only two parameters, it cannot fit into the three data points, right? And when you add the number of data points also, it cannot fit very well because the model cannot fit into all the data points with its capability, right? The capability is its number of parameters, right? So it is actually a part of its capability, right? So it has a particular certain pattern catching way which is inherent to the algorithm, and also it has this is like the amount of memory, right? The number of parameters are relevant to its memory. If the memory is 2, it cannot keep the information of 3 data points, right? That is the idea. So when you think about machine learning is kind of a data compression algorithm. That means you in your memory also, you remember all this data in your memory, but you can't keep all the videos that you see day to day, but you sorry, keep some of the information which are very important in your memory, which is known as a lossy compression, right? That means you remove all the unnecessary data and then you extract all the necessary information and keep it in your brain, right? Thinking that your brain is also a machine learning model like this, right? It's a learning model, and your neurons are kind of relevant to, not exactly, but just think that they are relevant to the parameters, right? So then you have a number of parameters. If your brain is large, you can understand well, right? So you can understand complex concepts because you have enough memory neurons to model these nonlinear relationships that are caused by that are relevant to higher number of data points, right? When you have higher number of data points, if you want to model it into your machine learning model, you may think that that you need more memory, right? That is how you think, right? Okay, but actually this may not be always correct. What do I say? What should I? Do you understand what I say? So you want to understand the complex concept. That doesn't always mean that you need a higher amount of memory. What do you mean? Do you understand what I say? Suppose that you get a certain data set, right? Where you have the relationship like the physics relationship like F equals ma or something like this, right? So it is a it is like a small algorithm, right? Machine learning algorithm where we can model it with this kind of straight line y equals mx plus c, right? So, but all the data that you have with all the moving parts in your machine can be modeled with f equals ma physics theory, right, from Newton. So when you know this mathematical model, when you know this physics function, physical relationship, it needs only a single parameter actually, because the intercept is also zero. The zero, the plus c part, the c is zero, right? So you don't need to have c. You only need m to find the acceleration of a particle. When you know, when you get the acceleration, you can get the uh, force, uh, and what you have to know is the mass of the particle. If you don't know about physics, don't forget about it, right? So what I say is that if although you have a lot of data, you can actually use a very simple formula to learn how they behave uh, in certain cases. But in certain cases, it is not the case, right? For example, if you want to predict the market, like financial market, then you will not be able to use a simple formula like this to predict the market price. So then you will need a lot of uh, parameters, right? So how the model is fitting into your data also depends on parameters, right? So when it comes to the power of affecting on a particle and how it is accelerated can be modeled easily. It can be highly fitted very accurately with only a single parameter. But when it comes to the market, financial market data, it cannot. You may need a lot of parameters to fit into your model, right? And when you have a lot of training data also, your model's fit may get changed. Say you only have 3 data points, you can use a uh, model like this, right? Y equals beta 0 plus beta 1 x plus beta 2 x square, right? This line. But when you have even more data, right, like this, those data points, all these data points will not be uh, predicted accurately with this 3-parameter model, right? Actually, using these 3 data points to model and using the 3 parameters to model these 3 data points is not the correct way, right? It is known as overfitting. So we will discuss it later, right? And we have also discussed about gradient descent, right? The way we are learning machine learning, the way we are fixing a machine learning model into the data set, right? So in gradient descent, for example, you have to iterate multiple times to fit your model into your data points, right? at the beginning, you may start with 0, 0. You remember what we have discussed. You can start with 0, 0, known as zero initialization, or you can start with the random values for each of these parameters, known as random initialization, right? So then your model will get changed little by little, right? So if you are using a polynomial model like this, and if you have only 3 data points, if you have run the model many times, many iterations, it would be fitting to all the data points with around 100% accuracy, right? But if you have stopped somewhere before, maybe you will have your model will be something like this. It's not that much fit into these 3 data points, right? This data point, this data point, and this data point. Your model may not have yet fitted. That means the model has not yet fitted into your data points accurately because you haven't run your algorithm many iterations as possible, right? So you may have stopped it earlier. So there, then the data points may not have fitted well, right? So you may find it is bad, right? So what we want is to fit the data, but it has not fit. But sometimes we will learn that sometimes that is good, right? So not fitting the data, not fitting the model into the data points as much as possible is a good thing, and we want to achieve it. So we may want to use this stopping algorithm, stopping early when it comes to iterative training models, like training algorithms like gradient descent. So number of iterations used for training also matters when it comes to the level of fitting into the data set. So there's another technique called regularization, which we are going to discuss. If it is applied, it can also change the change how much the model is fitting into your data points, right? So we will discuss it later. So this is actually what we mean by the model fit, right? So if you haven't understood in the earlier slide, this is where you can have to understand, right? So there we have explained it into types of supervised machine learning. First one is classification, and the other one is with regression, right? So suppose take this. So all these three graphs are the same when it comes to blue dots and beige orange color dots, right? So here in these three graphs also you can see the same. Remember that all the data points are the same, right? So here also these three graphs have similar data points for all the blue color data points and the orange color data points, right? So in this case, in this classification problem, what we want to do is we want to classify the blue data points and the orange data points. And that means we want to classify them into 2 different classes, right? Which is known as binary classification, right? So in these 3 cases, right? This one, and this one, right? We have 3 different classifiers. So this black line defines the classifier, right? This is the classifier here. This is the classifier here. You can see what we want as a classifier, right? So just look at this data points, right? How this blue data points and orange data points are distributed, right? So there's no specific boundary, a clear boundary, right? So when you want to make a machine learning model, when you want to train a machine learning model, what you should expect is something like this, right? That means that with this decision boundary, there can be certain uh, misclassified points like these points for blue data points, and like misclassifications like these orange data points. But what we want is a smoother curve, right? Not too smoother like this one, and not too rippled like this one as well, right? So when it comes to this model, this line is a very simple line, right? Like a logistic regression with the with linear uh, parameters, with linear, yeah, features, right? Without using polynomials. So here our descriptive power is lesser in this model, right? That means it cannot, that there are too many misclassified data points, right? So when it comes to this side, there are many, right? And this side also there are 2 data points. It is not that good. When it comes to this data, when it comes to this classifier, you may think that it is good, right? Actually, it has classified 2 classes with 100% accuracy. Can you see it? All the blue data points are located in this side, and all the uh, orange color data points are located in this side of the, from the decision boundary. So now you see it kind of weird, right? So its decision boundary has gone too much way to classify these 2 classes. So this is not something we expect, right? Why? Because when we try to classify these 2 classes like this for the training data set, so then you will find difficulties when you want to classify the real world data. So here what you have tried to do is you have tried to classify as much as possible. That means you have tried to maximize the accuracy. That means you have tried to fit your model 100% into your data set, but that won't help because this model will not fit well into some other data that are not in this training data set, right? Suppose that you are using it in the production environment. That means for real world data that we are going to predict from this model will not be having this kind of complex distribution, right? So here you see these data points that are moved into the region of the orange data points that are in the blue class, and these blue data points that are in the partition of the region of orange class are kind of noises, right? So if you have this kind of noise data in your data set, what we really expect is to ignore the noise and make a smoother curve, right? Not too smooth, but fairly smooth, so that it can classify these 2 classes, but not too curvy and trying to fit too much and classify in extreme way, right? Because once you have developed the model like this, when you have real world data like say you want to classify a orange data point, something like new orange data point, something somewhere here. So using, if you have used the model like this, it would be classified as an orange dot. But here what happens is, it had, because of this ripple, it will classify, the model will classify this data point as a blue data point, which is not correct, right? So when you have this kind of highly rippled classifier, it is not good when it comes to fitting into the real world data, right? This one is not good because it doesn't reflect the distribution that much. It is too simple, right? It is too simple. It has a lesser accuracy. So you should be focusing on that as well, right? You have to focus about accuracy, which is known as bias actually, right? And in this case, you have to say that you have higher variance, right? So fitting too much is known as overfitting, and not fitting at all because of the simplicity of this classifier, it is known as underfitting, right? And fitting correctly as the way we want, it is known as the right fit. And this is how the classifiers types that we will have when we are having different types of algorithms, different number of parameters, different amounts of data, and different number of iterations, and the amount of regularization used. So this is also applicable to regression as well. So I haven't explained, but you can understand, right? So when you want to model this kind of data points, what this kind of line is, this kind of regression line is what we expect. This kind of straight line is too simple, so it can't model this curve, right? But this kind of crippled regression line is too much. It is trying to fit too much into the data points, but it is a unnatural thing. So it is known as an overfitted case. So this is also bad. So this one and this one are bad. This one and this one are bad. This is what we want. This one for classification and this one for regression. These are the two that we want to have in our machine learning model training. Right? Do you have any questions up to now? If you have any questions, you can unmute and ask, because I can't see your chats because I am in full screen. Do you have any questions? Okay, so I will move into the next part, which is known as the definitions of bias and variance. So these are not the exact definitions, but this is how you should understand the concepts, right? When a machine learning model cannot make the predictions correctly, right, because the model is too simple, right? So if it has to, the model has only few number of parameters, in this case 2 parameters, right? In the y equals mx plus c case, there are only 2 parameters, m and c, right? Because the model is too simple. In this case, this may be a quadratic line, right? This line may be following a quadratic equation. So this one is better. This one may be having a higher degree polynomial, like the degree of 8 or 10 or something like this. So this is also bad. So when it is too simple, the model is too simple, when there are too few parameters to learn into the data, there will be a bias. That means you won't be able to understand what is really there in the data. So because it is too stupid or it is too unintelligent. So this is known as the bias problem. In the case of overfitting, right, you can have, in suppose this is a 8-degree polynomial, it has too much parameters, but too much parameters would increase the variance of this case, right, which should create a this overfitting problem known as the variance problem. So what causes what is the bad thing about variance problem is that in the variance problem, this machine learning model would be very good at predicting the data in the training set, right? So this is the training set, and what happened was the model has overfitted into the training set. So when you have new data like the data from the test set like this, it cannot predict correctly. In the variance problem, what happens is the machine learning model is very good at making prediction on its training set, but very bad, or bad means has a larger error for real world or unseen data. So in this case, we can test how much the variance it has using the test data set, right? Because the test data set represents the unseen data for a machine learning model, right? Unseen data means the data that is not used for training. So this model is created because of training, right? So once you have trained it, the model can fit into all the data points that are used for training. But then when you introduce a new data point from the environment, like the data point from the test data set, we can identify what is the real accuracy it would be having when it comes to unseen data. Right? So you can find this is the variance problem when there is overfitting. When it is underfitting, we have bias problem. So when you are training a machine learning model, you should try to minimize both of these problems. Right? We will discuss it, the problems that you have and what to do with it. What you have to do is you have to reduce both of them, sometimes one of them first and another second, or maybe both, depending on the case. Right? This is another form of explanation for the errors of bias and variance. Right? So now you know that bias is an error, right? Variance is also an error. Suppose what you want to do with the machine learning model is to throw darts, right? You know what a dart, right? A spiky something, right? Which has a sharp point, and you are trying to hit into the target, right? Something like this, right? Then you are trying to hit into this target using a machine learning model, say, right? Suppose your machine learning model is very low with variance and very low in bias, then it can hit the exact target very well, right? So that this is the best case. That is what we want, right? Suppose it has a lower bias, right? So that means the machine learning model is not too simple, right? And it doesn't have any bias. The bias means a, a deviation from the uh, expected value, the correct value, right? That is another interpretation of bias, right? So if there is no bias and there's only variance, variance means the data can be the outcome can be subjected to change with the data, with the type of data, right? That means your data may be very good at training data set, but when you introduce new data for predictions, there can be a lot of differences, lot of variance around the expected value. So this is the expected value, right? Expected outcome, but there is a huge variance around this expected outcome. If you only have the problem of bias, what happens is, and not the variance, low variance, but high bias, there's no spread of your data, right? Your data is not spreaded because it is not, there's no less variance, but you have a bias. Bias means it is deviating from the expected point to a certain degree. It will hit the target in nearby locations, but because there's no variance, but away from the target. This is known as, this is the interpretation of high bias but low variance case. When you have higher bias, both higher bias and higher variance, your darts will be centered around somewhere away from the expected point, somewhere here, and it is dispersed, or it is there's a variance around this expected point to when it comes to the points where the darts are hit. This is the problem with high variance, with high bias. This is another interpretation of you to understand bias and variance. Right? So you may think that, right? So less amount of parameters would create this kind of deviation. How is it happening, right? So what it means is that when you don't have enough parameters, there won't be much dispersion of the model. That means the model will be very robust, right? For example, if you are using a linear regression, when you introduce more data, there won't be much risk involved with the model, right? So if your model is has very high number of ripples, there will be a higher risk. That means where your data will not be hitting the target, right? But when because it is a linear regression, it will always have a bias. That means it will not be the exact point, right? But if you have a high variance model, it would be in the different kind of error, right? Like this, where you may have less bias, but if there's some variance, the data points that are resulting will be taking a larger space dispersed each of them from the target. So this is the nature of bias and variance. So let's compare again how this underfitting case, or known as the bias problem, and the overfitting case, known as the variance problem, are different from each other, right? So I am trying to explain the difference and how they exist in different ways, right? Don't get confused. These are very simple concepts, but the way we have to understand is may need some more information, because this concept may not be straightforward if you haven't got it completely, right? So in the first case, The underfitting can happen when the model is not complex, right? So we said that, right? Said that, right? When you have less number of parameters, the bias problem can be happen. And when the number of parameters are too large, then it can model fit to all the data points. But that is for the training data set, right? Once you have trained, it will have a very low error for the training data set. But when you test it with the testing data set, you will have a very high error, certainly certain kind of larger error, right, relative to the testing to the training error, because the data set, the model has overfitted into the training data set. So when you meet with some other data away from the training data set, you will have a higher error. You can check it with testing data set, right? The bias can be due to undertraining, as we mentioned earlier, right? When you are using a iterative learning algorithm like gradient descent, suppose you have to wait until the cost function is reduced, cost function change is reduced up to a certain level, a smaller level. That is the way that we have discussed, right? So that is the point that you have to stop training. But in some cases, you may have stopped it earlier, right? That means your model is not yet fit into your data set. So that may also cause underfitting, which is known as the bias problem, which causes the bias problem, right? So, and this is actually related to much complex machine learning models like neural networks, right? So if you train it too much, the neural network will fix too much into the data points, and it would cause overfitting, right? So if you have too much parameters and if you train too much, that means you see that your training data set error is reducing more and more, and you try to minimize this training data set error. Now what happens is it has fitted very well into your data set, but the problem is now when you try to test it with the outside world data, the test data, it would have a higher error, which is known as the variance problem, right, which has caused due to overfitting. So the problem, and what happens is with underfitting, this accuracy would be lower, right? For example, if you use a linear regression for modeling the financial market results, there would be lower accuracy, right? Because you are trying to model a very complex system with lesser number of parameters. So this causes the bias problem. On the other side, if you are trying to model a simple thing like you do some test with F equals ma, right? Like the force and the acceleration, and you get some different values, and you try to model it using 8-degree polynomial regression, right? So you have 8 parameters for the 8-degree polynomials. So what happens is when you take the measurements, you would have some errors, right? So what happens is this 8-degree polynomial would fit to all the errors that you have come up with when you are taking the measurements of force and acceleration. So this would create overfitting, and when you have tried to predict a new data point, like when you have the acceleration, when you try to predict force, you will have much higher error with your model because you have used too many parameters, which has caused overfitting. Right? With bias, the problem is lower accuracy. That means it would have a lower accuracy in both training dataset and the testing dataset. So when you can simply see it like you have a higher error in the training dataset, and if you test with some other data like the testing data, you will still have a higher error. That is how you can identify the bias problem. But so the problem with overfitting is, or the variance problem is, it would fit much accurately for the training data set, but when you see the outside world data, or when it is trying to generalize into the real world, it is not generalizing. It has generalized, overfitted into the data it has learned. Right? That is the problem with overfitting. So you can actually get these two concepts with related to humans as well, right? So higher bias people are like less intelligent people, right? So because they have not enough, maybe they have lesser activity in their brain, so maybe most of the neurons are not working, only few neurons are working, kind of thing, right? So I am not a neurosurgeon, human neural network expert, but that is how you have to understand it. So you have a lower IQ, and because you are thinking in or everything as simple stuff, right? And you can't understand very complex things. You try to model very complex situations in a simple way, right? So for example, if you try to uh, model a very complex geopolitical issue, and suppose you are trying to reduce it into a certain kind of religious, or just some certain personal anger or something like that. So maybe that is related to higher bias, right? So you don't have enough capability. No, actually, this is not related to. Don't take it personal, right? So I'm just giving some example, right? So when the problem in the real world is too complex, but the brain has less amount of parameters to learn it, your brain will try to uh, model it, but not. It will have lesser accuracy. But the advantage is that when you have uh, any type of problem, you will have some solution, right? So you would, because your model is simple, your simple model can actually find solutions without much increase in error, right? For example, if you have a very complex geopolitical issue, you will predict it with some your social, something that is personal to you. But with the same model, you may be able to model when something happens in your when there's a conflict with your friend or something, but still you would have a similar kind of error. That means you will not be thinking too much deviating from the real problem, right? So you will have an error, but that this error will not be increasing too much when the data points are changing, right? So that is the advantage of having higher bias, right? So when you see a conflict, you see all the conflicts as similar kind of stuff, right? So you think that this is because the other person don't like me, so I should fight it again. So that kind of very simple way, right? I have to fight back, kind of thing. So, but that may be working up to a certain extent, right? So it is working for almost all the situations, like when tiger comes into you, you see same thing, right? So either I have to run or I have to attack. You can apply it in all the cases. But in the high variance people, so they have they have learned a lot, and their thinking is too much complex. And if they have learned a little, right? So what happens is, so they have less amount of experience. Now what happens is, uh, because they have a higher brain capacity, intelligence capacity, so they are trying to uh, identify all the everything that has everything that they have learned, and they model the real world like the exact same way that they have observed, right? And when something happens, uh, they may have some very complex outcomes. The problem with this one is that uh, it could work really well for the, so if the same thing that happened in the experience has happened again, that means if you are using the same training, like you are using the data from the training data set, but if you face some other outside world problem, you may have a very uh, high error, or the decisions you take may be highly diverging from the actions that you should have taken, because you have created your own world inside you with the knowledge that you have gathered. So that is the overthinking, and you are kind of living in an illusion. That kind of person is a high variance person. So this is just, there's nothing like this in psychology, but I'm trying to give some analogy to you for you to understand what is the difference. Right? Okay. So what is bias? So we will try to move into the formal definitions now. Right? Uh, the bias is caused by not learning enough of the insights of the data set by the model. Right? So, because it has a lesser amount of parameters, and it is not that much capable of fitting well, what happens is, uh, it is the model is, it is known as less expressive power of the model, right? Less expressive power means, lesser expressive power means uh, it cannot model the complexities in the data set. That is the problem with bias. So this, because the means there are, the model is less complex or less number of parameters, it cannot uh, maintain enough information of the data distribution. So you need a lot, some amount of memory to keep the information of these complexities of the data set. But when there's high bias, when you have, because of you have having lesser number of parameters, it cannot create all the information. It would create only the most relevant, most significant information in your data set, in your training model. So you would make decisions on that, and because they are highly significant, uh, it won't create that much error time to time. That means the decisions they take will not have a higher variance, but because there's a high difference between the reality and the decisions, it would have a higher bias, right? So, so this is what I have discussed. Right? So in the gradient descent is may grows due to finishing the training process before completion. So this is the formal definition of bias, right? The fx, when the function that we are going to predict is fx, and this is the expected value of predicted value, and this is the real value known as the ground truth value, and this is the difference between the expected value of predicted value and the real value is known as the bias, right? So how to reduce the bias? Bias can be reduced by using better machine learning algorithm. So there are several ways that you can reduce the bias, right? So you can use a better machine learning algorithm. For example, if you are using a linear regression, a linear classifier, right? Something like the logistic regression without polynomials. So what would happen is, suppose that now you are having a higher bias. Now you would have to use much higher degree polynomials. So by changing the algorithm, or you can use some other algorithms that are having a higher fitting capability, like support vector machines. So we will discuss it them in later, right? Or you can use a larger model, right? So with more parameters, like I said earlier. So when you are using a linear classifier, which should be having two parameters, you can increase the number of parameters by using polynomials. And with this kind of larger model, would be fitting more into your data and reduce the bias. And if you have stopped earlier when it comes to training the model with an iterative method like gradient descent, you could have you can stop you can stop it earlier. And so this is actually true mostly in the cases of neural networks. Right? When it comes to training neural networks, this neural network is a cost function that we are going to minimize, right? As we have learned in gradient descent. This cost function is very complex. Because of that case, it may take a lot of time to reduce the cost function. So sometimes we may stop earlier to reduce the computational requirement. So if there's too much bias, you can do more number of iterations, which should reduce the bias, right? And this may also caused by using limited amount of data, right? Suppose that, for example, you want to model the financial market prices. You only use 10 data points. That is not sufficient, right? 10 data points doesn't contain the information for the machine learning algorithm to absorb all the information related to the market, right? So you need much more data when the model is too complex, right? Or the model contains much information. You may need to have more data to train the model. If you are using less amount of data, you will be having the bias, right? As we said earlier, so the thing we will be discussing today, if we are applying the technique known as regularization, we can reduce it. So we will discuss it later. So when it comes to an example, you can say that when the data are following like order like this, right? Data are located like this. In the space. So what we need to model these 4 data points is straight line, right? Straight line. But suppose now we are using a polynomial regression, quadratic polynomial, you would have a much say not a quadratic, say the 5-degree polynomial or something. So then it would be like this. It will try to fit to all the data points because it has too much capacity to capture all the information in the data points. But this seems good, but only for the training data set. But when it comes to real world data, this is a high variance case, and it would create an error due to the higher complexity of the model. So the variance, no, it right, variance is introduced when the model is too much fitting into the training data set, right? And the problem with the problem is caused by the variance is due to its the noise in the data, right? So if there are no data, or there are no noise in the data, then there won't be a problem with variance. But in all the cases in the real world, there are noise in the data. So when you have noise in the data and you have much more parameters that you have used for your model, or your model is too complex, the model will try to fit into the noise as well, because it has much capacity to absorb the information from the data. It would not only capture the information that is relevant, like the more significant information, but will also try to uh, absorb the lesser significant information as well. In most cases, the lesser significant information are related to the noise. So that is how the variance is affecting badly when you have too much complex, you have much complex model. So this is the formal definition of variance, where the variance of the fx is known as the expected value of predicted value minus predicted value square and the expected value of that value, right? So the idea you have to get is that it is like it's a kind of mean square errors, not like that, right? So not in, it is not the hat, right? What we are taking is, we are taking the expected values of not the average of y, but the expected value of predicted values and the predicted values, right? So something which is proportional to the square when it comes to the dimensions of the y variable, right? So when it comes to physics, you may want to understand it, right? So you are using, this is a square relationship where you are taking the expected value. So if you don't understand what I have just said, just forget it, right? So this is just the formal definition. I have mentioned it because it is required. Otherwise, you won't have need this formula to make calculation, right? You are not asked to write calculations. What you have to do is, you have to identify when the variance happens and when the bias happens, and what to do when it is there, right? So how can you reduce the variance? The one way of reducing the variance is by using a larger training data set. When you use a larger training data set, uh, because you have a limited number of parameters in your model, these parameters cannot fit into the given data set, right? It is something like this. If you have 3 data points, and if you are asked to do a quadratic relation model, to model it with a quadratic model, so what would happen is, it would try to model it like this, right? But suppose now you have much more data. Now you can't model it like this, right? So you have to think about other data points as well. With the quadratic, even with the quadratic model, you can't draw a line in a line like this, right? To generate a line like this, because there are other data points as well that you have to consider, other data points. So it would be something like something that would be much better, right? Something like, maybe something like this. There would be some curve, but still it would be much better than this one, right? So when you increase the number of data points, you will have a better model with reduced variance. So here what has really happened was that the errors has got cancelled out. So if you think like that, you can understand it. Don't think too much about it, right? So what you have to understand is that when the variance is there, and you have a higher variance, maybe you can, if you can get more data, you can do it, right? That is the best thing, right? So having more data, when you have the opportunity to get high quality data, don't avoid it, right? So unless you have some problems with computational limitations, like for example, you don't have enough powerful computers or time, or you don't have enough money for the infrastructure, then you may be using some small amount of data. But in all the other cases, use data as much as possible, which would reduce the bias as well as the variance, right? So that is a rule of thumb, right? So if you have enough high quality data, right? So if you have lesser quality data, maybe you can have to think twice whether I should use this low quality data for training our model, right? And then reducing the number of parameters can also reduce the variance. So as I mentioned earlier, because when you have too much parameters, this extra parameters would try to absorb the noise in the data set as well. When you reduce the number of parameters, it would only extract the more significant information in the data set. In most cases, this more significant information, more significant patterns are the patterns that we want to model with our machine learning model. So that is how we can achieve it, by reducing the number of parameters. Right. So if you have learned about dimensional reduction techniques, dimensional reduction means nothing big, right? So if you have, suppose you have x variable, x1, x2, and x3, you want to reduce. So there are 3 variables. Now you find that from exploratory data analytics or something, that 2 variables are interrelated to something, and then you use some algorithm like principal components analysis, PCA, which is also a type of dimensional reduction algorithm, and you can get 2 new parameters like x4 and x5. Now you can use these 3 parameters to train the model instead of these 3 parameters. So now reducing the number of dimensions from 3 to 2 is known as the dimensionality reduction. So PCA, or principal component analysis, is one of the dimensional reduction algorithms. There are some other algorithms as well, right? Like when it comes to neural networks, there are things like autoencoders and so on, but here you don't need to know about those things, right? And the early stopping, right? So we explained earlier, right? When you're using an algorithm like gradient descent, you can stop early, so it will not learn the fine-grained details of the model, of the data into the model. So that is another way of reducing the variance. but that has some issue, right? Don't you think? So early stopping or training lesser number of iterations would actually reduce the variance, right? Because it so only if you train many times, the model will get fit more and more into the data points. But if you train only few number of iterations, it would fit lesser. But that is not good, right? Because then it won't be able to get the even the expected amount of information from the data set if we train it lesser, right? So training lesser is not a good thing to do, but it can also be used to reduce the variance, right? So we will discuss it later, right? So without stopping early or without reducing the number of iterations, you can use other techniques like regularization and uh, like regularization, increasing the regularization. If there's no regularization, you can include the regularization. Or in the case of neural networks, there's another type of variance reduction technique, or another type, you can say another type of regularization technique known as dropout. We will not discuss it here, but I have added it here for the completion. Right. So in dropout, what happens is in the neural networks, you have several layers of neurons. So those are connected with each other. These neurons, these are layers, right? These are layers. These are individual of these dots are related to neurons, right? They are connected with each other. So when you are training, each of the neurons are trained together. So some of the, when it comes to dropout, what happens is they randomly select some of the neurons and switch them off. For example, you switch this neuron and train only this neuron at a certain iteration. And then in another iteration, you switch this one and this one off and train only this neuron, kind of thing. So that is known as the dropout regularization. We don't need to learn it in this lesson. Right? And when it comes to an example, you can say that if you are trying to model a linear model with 8-degree polynomial, that is a that would introduce variance into your higher variance into your machine learning model. Okay, so now we have learned that actual about little bit about bias and variance. If you try to graphical represent it, you can say that when the model complexity is increasing, or you can say according to what we have learned, so model complexity is related to the number, maybe related to number of parameters, right? Beta parameters. So if when it is increased, the model complexity will get increased. When the complexity gets increased, the bias will get reduced, right? But when the bias get reduced, the variance will get increased. And from here, you can get the mean square error is the bias square times and plus the variance. VAR is the variance, is the bias. The bias square plus variance is the mean square error. And for the prediction, we can get mean square error plus this irreducible error. So there's another constant which is known as irreducible error, which is the error that is not relevant to the bias or the variance, but an error that cannot be reduced with the techniques that we discuss here, right? So that is constant, but that is not affected by the that is not relevant to the bias and variance. So the total error is defined. The square of total error, expected value of the square of error, is the addition of bias square plus variance plus the irreducible error. So the total error would follow a curve like this, right? If you have learned about the number of iterations and the number of iterations in this gradient descent and the amount of error, you might remember that this is the test error, right? This is the training error. So this test error is having a curve like this total error, right? So because this total error is the real error, that the error that you are getting of unseen data from the environment. The training error, on the other hand, will get reduced again and again because it is overfitting to the data set or the training data set. Although the bias is getting reduced, the variance is getting higher and higher, and the error for the training data set will get reduced more and more. But because the true error or the test error is the sum of bias square plus variance and the irreducible error, in the first stages, the error is reduced because the bias is reduced when the number of iterations are increased. So this is about number of parameters. So this is about increasing the number of iterations, right? So both would have a similar effect on your trained machine learning model, right? So both will increase the amount of fitting, right? So number of parameters will also increase the fit, and the number of iterations will also have the effect of increasing the fitting. So at a certain point, you would have the optimum model complexity or the optimum number of iterations. So these iterations should not be limited in most of the cases, right? But in certain machine learning model, like complex neural networks, you may be having this kind of scenario, but in general case, you don't have that much concern about reducing the number of iterations. You have to do it as much as possible, and you have to apply another technique that we will be discussing later in this lesson, known as regularization, to reduce the variance instead of reducing the number of iterations, right? So for the reducing the number of parameters is also not that advisable, because reducing the number of parameters means you will not have enough capacity to capture the information from the data set. So instead of reducing the number of parameters or reducing the number of iterations, maybe you can do, the best thing is, first thing you have to try is whether you can use more data. If that is the case, you should go for that. If there are no more data, you have to use regularization. Right. So now we have discussed, and you might have already understood, that there's a trade-off between bias and variance. Right? So when you have a lot of parameters, you move into you would reduce the bias, but you will get more variance. When you have more data, that would not be having that much issue, right? But in the number of iterations also, there are some effect on the fit, right? As we have discussed earlier. And regularization would also have an effect we will discuss later, right? So we may be able to try, if you don't know about this trade-off, you might have try to tune all these parameters, like parameters, data, and the training iterations and regularization to reduce both bias and variance. But because there's a trade-off, once you reduce the bias, the variance is increased, and the in, uh, variance is reduced, the bias is increased. That is the problem. So this is known as the bias variance trade-off. So what we have to do is we have to come to a compromise between bias and variance. So this is not a universal truth, right? So just remember, right? So there's this concept of bias variance trade-off, right? But when you this is a universal truth for machine learning. For example, if you have more data and if you can increase your model complexity without much adverse effect, the best example is neural networks, right? You can increase the number of data with the currently available big data, and you can increase the number of neurons in the neural network. In that case, you can actually reduce both bias and variance together. Right? So, but here what we are discussing about bias and variance is about the smaller, very simple machine learning models, right? So this is a not universal theory, but generally, when you have some restrictions, like for the amount of data that is available and so on, then you may be having some issues. You may you may face this bias variance trade-off, right? And this is the early stopping, right? Early stopping means that the testing error would be like this, right? The training error would be like this. The number of epochs. Epochs means the number of iterations, right? This is the number of epochs or number of iterations. And this is the loss or the error, right? Loss is, you know it, right? It is a measure of error. So the training error would reduce more and more. It would indefinitely, monotonically, we call it as monotonically fitting or monotonically reducing the error for the training set. But for the testing set, the error or the loss should reduce a certain point, and then it should increase again. So if you want to get the optimum amount of the least amount of error, you can stop here. So not this point here, this point, right? This point where the testing error is minimum, you have to stop. This is known as early stopping. This is not that much recommended way because it would avoid the model from learning the information, right? Depending on the starting conditions, right? So if you have started in some unfortunate way, like with random variables that are away from the optimum value, you may be stopping somewhere away from the optimum point. So this is not a good way, but it can also be used. So this is the technique that we use in this kind of situation, right? So this is known as the regularization. So when the high variance is observed, right? So when the bias is observed, but you know what to do, right? You need to increase the number of parameters, increase the number of data, and so on, right? When you see when you see the variance, what you have to do is you have to first thing you have to do is you have to find data, but in most cases you will not find any more data than the data that is available to you, right? And then what you have to do is you can reduce the number of parameters of the model. Like maybe if you are using a linear model or something, you can reduce the number of input features with using a dimension reduction technique like principal component analysis, right? As I have explained earlier, and try to reduce it. But and also you can use some feature engineering techniques, right? So we will actually discuss some feature engineering techniques in the future lesson. But those things may not be obvious for most of the scenarios, right? That means you will not have, because you are not a domain expert. Here you are a machine learning expert, so you may not have the knowledge about the domain of the data, the field, the domain of the problem domain. For example, if you are using a medical data set, you may not be a consultant physician to know about the diseases. So you may not be able to do the reduce the number of parameters efficiently. So if you reduce some of the parameters, you will get lesser accuracy because you are losing useful information on the model. So the technique that we are going to use in this kind of scenario is known as the regularization. So the regularization is a technique that we apply in each of the iterations when we are training a model, right? So what happens in the regularization is we are trying to add some penalty into the loss function, right? So in each, you have learned that the gradient descent, right? You are in each point you are having a cost, right? Each iteration you have some cost for that particular iteration. In each cost, you can actually add some more cost depending on some of the parameters what we assume that are relevant to the noise, right? So things that we think that they are not relevant, we can add more cost or add more loss, right? By adding more loss, cost is the addition of loss for all the data points, right? So you can add some more error add more loss into the loss function in each of the iteration, and that is known as the regularization. This is how we do it, right? So we add, so when we get the value for the loss, we add some value, add this term into the loss value in each of the iteration. So now look at it. So this lambda is a constant that we have to define. It is known as a hyperparameter where we have to set it from the beginning of the machine learning process. And this is the n is the, suppose this is the number of features in the data set, right? Beta is the parameter of the model. So n is the number of parameters, right? So what you have to do is you take the kth power of this beta parameter and get the addition of all these beta parameters, kth power of all the beta parameters. Actually, the absolute value of kth power of beta parameter, get the sum and multiply it with this constant, which is generally defines the regularization strength, right? So lambda is known as the regularization strength. So you multiply this term with the strength parameter, which we have already set at the beginning, and then we add it into the loss. So using this technique, you can add the regularization into your model, where you would be able to reduce the amount of overfitting to the data, right? So this k value is can generally have two values, like either it can be 1 or 2, right? If the k value is 1, you just add the exact parameter, use the exact parameter, and that is known as the L1 regularization or lasso regression. If the k is 2, we take the square of the beta parameter, and that is known as the L2 regularization or ridge regression. Right? So let's discuss what is the L1 regularization, where you have this beta parameter only, and you take the absolute value of the beta parameter for each of the beta parameters, and you get the sum and multiply with the regularization strength and add it into the loss function. Right? So this penalty is proportional to the sum of parameter weight. So this is the parameter weight, because you don't take it into any power. It is proportional to the sum of parameter weights. So this is also known as the feature selection. It does select features, right? So what happens is less significant features will be moved to 0 when you are applying this kind of L1 regression or lasso regression in your machine learning model, right? So suppose that you have I values that for different parameters. The parameters that are less significant, that means that are less in number, will be reduced more and more, and they will go to 0 depending on the lambda parameter that you have selected, right? So why we are using L1 parameter in which kind of scenario? So we are using this L1 or the lasso regression when we believe that there are too much parameters. Some of them are not relevant to the model, which has lesser impact. So we want to remove those less significant parameters from the model and simplify our model. So this would eliminate all the unnecessary less significant parameters and select these features, right? So when it comes to, so this is known as the feature selection algorithm if we are using this L1 regression. So how many features are getting into 0? That depends on the value of lambda. If the lambda is larger, more and more features will be 0, and lambda is too large, all the beta parameters except beta 0 will go to 0. So beta 0 is the intercept, right? So beta 0 will not be applied to this regression. So I started from 1. So beta 1, beta 2, everything will go to 0 if the lambda is too large. Only the beta 0 will be remaining. So the other parameters will be eliminated if you apply a very large for this regularization strength in lasso regression. So the second type is the ridge regression or the L1, L2 regression. We had the lambda times beta 1 square. So the error is penalty is proportional to the sum of square of parameter weights. So instead of using the absolute value of parameter weight, we take the square of the parameter weight, which is also a positive number, and multiply it with this constant and add it to the loss. So this is known as the weight decay, right? So why we are using L2 regression, L2 regularization? So we apply the L2 regularization in an assumption like this, right? Suppose that we think that there are some features are too large, but they cannot be too large, right? So that means, so the idea is that in certain ways, depending on the initialization, there can be some features that are too large, and we assume that none of the available features are too much significant. That means all the features that are given, they are like the parameters represented by beta, all of them have some impact on the model. So we should not let the highly significant parameters to take over the model and eliminate the effect of other beta parameters. So when we apply this L2 regression, what happens is when you have larger values for beta, the square would be even larger, right? So when you have larger amounts for larger beta parameters, there would be a huge penalty added into the loss. So the larger beta values would be reduced. The smaller beta values would not be reduced that much, but all the beta values will be reduced, but they will not go to zero. Right? So the difference from the L1 regression is that in the L1 regression, some of the beta parameters, beta parameters will go to zero, but in the L2 regression, none of the parameters will go to zero, but all the parameters will be reduced, especially the larger parameters. The larger parameters will be reduced more, is known as the effect of weight decay. Weight would be decayed from larger values to moderate values, right? And the the lambda is the parameter which is affecting this strength of this L2 regularization. If lambda is large, the beta values would be reduced more, but still, how much larger the lambda is, the beta values will not go to zero like in the L1 regression. So there's a difference, right? So in the L1 regression, some of the beta values will get zero. When the lambda is increased, many number of beta parameters will go to zero, but in the L2 regression, none of the beta values will get to zero, only they will get reduced, and the larger beta values will get reduced more, and that is the effect of L2 regression. So there's another type of regression known as the elastic net regression, which is a linear combination of both L1 and L2 regression. So instead of using in this elastic net regression, what we are doing is you are selecting a parameter known as alpha and apply it into alpha times L1 regularization plus 1 minus alpha times L2 regularization. Alpha times L1 regularization, 1 minus alpha times L2 regularization, where alpha is also a number which is between 0 and 1, right? So now you see it, right? So by adjusting the value for alpha, you can tune how much of L1 regularization should be applied and how much of L2 regularization should be applied. And this is the loss function, right? So you can take the lambda out, and this is how it is, like this. So you can select a suitable alpha value to tune the L1 and L2 regularization, where both of them are applied at the same time for the loss function. Okay, so this is how we apply the linear regression for so this is how we apply L1 regularization for linear regression, right? So for the let me yeah, so this is the line, this is the J beta value or the cost function for linear regression, mean square error plus this error term, right? So this is for the L1 regularization, and when we replace this MSC with the value that we generally define, right? This is the representation of mean square errors, right? Instead of dividing by n, can you remember, we divide by 2, right? And this is the value for L1 regularization. And when you take the derivative of beta j, this is the value we get. And this is the value for linear regression for L2 regularization. Yeah, we have beta square, beta j to the power 2, and we add it into the mean square errors, and we replace the MSC with its value, its represented value, and then this is how what we get after getting the derivative j beta with the value of beta j. This is what we required for. This is the value that we want to have with when you are doing the gradient descent, right? So now you understand. In the earlier case, so you have only so yi minus y hat to the power 2. Instead of that, that 2 has gone. Instead of xij is added and the lambda is added as a, so this is multiplied with xij and the lambda parameter is added. In the L2 regularization, the same thing happened, and instead of lambda, lambda times bj is added into the into this derivative value, right? So this is the values that are L1 and L2 regularization values that you can get for logistic regression, right? So from the linear regression and logistic regression, you can see both are the same, but for beta, so you can see it carefully, right? So later you can see it. This j beta values cost function for L1 and L2 are the same, and the derivatives are the same, but what is difference is that this y hat equals f hat x, which is the function, activation function, the link function is different from the linear regression where fx is a sigmoid function, the logistic sigmoid function or the logistic function when it comes to logistic regression, but y is equal to x y hat, this f hat x is different. It's just the linear combination of beta transpose x only for the linear regression, right? So you can remember for the linear regression, fx is in the vector notation beta t x, right? For the linear regression. Logistic regression, fx equals no 1 plus e to the power minus beta t x, right? That is the only difference in between linear regression and logistic regression. When you see at these equations, both are the same, right? Okay, so that's all for today's lesson. If you have any questions, you can ask. Do you have any questions for now? Are you okay? Oh, so I will stop the recording so that we can start the tutorial session now.